Okay, good evening to all of you. We'll start the session now. Let others join up first. So, I think that so far, whatever which we have done are based on this syllabus of the course, whatever which we have planned. I hope that we have covered most of the things, starting from the introduction to math, from Mathematica. These are the topics I think most all of them have been touched, and then mathematical and numerical techniques with Mathematica, finding roots transcendental equation, different popular methods, convergence criteria, computation, complexity, random. The random numbers not able to touch, so that is missing. Okay. Then interpolation, slow fitting, then differentiation, and then numerical integration. Then integration of definite and indefinite integral applications. Also, we have seen ordinary differential equation, partial differential equation. We are going to start now, and we will be seeing some of the basics of this partial differential equation. Okay, and some classification of this partial differential equation. Some typical examples also we are going to touch upon today's class. With that, I think we will be completing about 20 lessons. I hope many of them have enjoyed the course, and maybe you can start use this Mathematica effectively or take some mini projects and try to work it out some of the things that we have learned based on this Mathematica. I hope you can really appreciate the power of this Mathematica by doing such many projects. Okay, so today's class will be on the PDE, partial differential equation, and these are the things which I plan to touch upon. Some little bit introduction to ODE because we have done enough on ODE and PDE, examples of ODE and PDE, classification of the PDE, few typical examples for the partial differential equations. Okay, so you might be wondering that this partial differential equation is, in my opinion, I think it's little confusing for people also, and it's rather tricky things. There are many tricky things are there, but once you understand that, then you realize how powerful these partial differential equations are, and they play a major role in many different areas in the science and engineering. Okay, there are wonderful things that can be done. And in fact, there are people, they have been working only on one particular type of a PDE throughout their careers. They are looking for interesting results based on this one type of a particular type of a partial differential equations, and they have been spending their almost entire career on that. There are so many interesting things that emerges even one single type of a partial differential equations. In fact, for a typical example, we all have been exposed to Schrodinger equations. Only one type, simple, time dependent and the space dependent. Okay, differential equation, but you can see that how much has been emerged. Okay, to understand about the microscopic world in terms of this simple differential equations connecting the time and the space. So like that, every one of the discipline or every one of this classification of the PDE itself is a big ocean, and there are so many things that are done based on such a simple PDE. Okay, so now we will show some typical example here. Here are the two different type of equations that are given. Okay, you can see here that ordinary differential equation have only one independent variable, that is x. So y is a function of x. So this is the one dependent variable. Therefore, this is an ordinary differential equation. Of course, we have more than one multiple variables that are available as independent variables. Then it will become a partial differential equation. Okay. So therefore, you find that the way the function what I have y of x becomes u now, y becomes u, and there are two variables. U is a function of x comma y. And I can have a 3, 4. Okay, there are many variables that's possible, but we try to limit it 2 or 3, and then within that there are many things to learn. Okay, so we try to understand some of them. So this is a typical partial differential equation in which you find there are 2 independent variables when compared to the partial differential equation. Okay. Now this partial differential equations, like ordinary differential equations, there are various methods to solve, but here you have to classify them first, the PD itself. Okay, and then try to look for the solutions and include all possible options in the every one of these PDE, and try to look at the solutions wherever possible analytically, and if you're not able to get analytically, look for the numerical solution. So here is the typical first order partial differential equation. Order what we refer is this, whatever the derivative which you have, that is the order of the your partial differential equations. For example, you have a dou u by dou x, dou u by dou, this must be y, not x, dou u by dou I, and then you have the other parameter along with that. Okay, this is the first order, first derivative, first order. This is also in first order. Okay, and there are 2 independent variables. In addition to that, there is a constant, or there is a variable a x y in the first term, and there is another variable here b x y, the second term, and there is another variable which is in the third term, which is a function of u of x y. If we have, that can also be there, but there is another term which is also associated with the u of x y, then equal to either this may be 0 or it can have a d of x y. Okay, where the d of x y is a forcing term. So the PD is linear homogeneous when this d of x y equal to 0. Okay, so you can see this, when this is 0, then we call it as a PD is a linear homogeneous when this the forcing term equal to 0. PD is linear non-homogeneous when this is not equal to 0. It's not a homogeneous equation. This is a non-homogeneous. Okay, now if PD is
So
quasi-linear,
why it is called forcing term?
it is sort of a term which alters the entire left-hand side of that. Okay, you have the terms like dou u by dou x, dou u by dou I, and other parameters. All these parameters can be get changed by this d of x y itself. So it is something like you might have heard about the so-called the ordinary differential equation in the damped harmonic. Okay, when this is equal to 0, it is a damped harmonic oscillator equation. But if you
Yes,
add
sir.
the right hand side some term, that's also like a forcing term. So the whole thing will be very much depends on the forcing term, is it not? The entire damped harmonic oscillator, whatever which you have,
Yeah, yeah.
that
Yes,
will be
sir.
controlled by what you have on the right hand side. Okay, similar term which is being used here, d of x y. When I alter anything here, the whole thing will be get modified. Wherever this you can see this will influence every one of the terms that you have on the left hand side, exactly like what you have in the damped harmonic oscillator. So sometimes they call it as a forcing term, which is when it is added, we call it as a linear, but it's a non-homogeneous when this is not equal to 0. And you can play around with this. Okay, there are many things that can be done. And here also you have different terms that are there. You can play with these things and try to understand more about this equations and their responses, depending on this d of x equal to 0, not equal to 0. Then PD is a quasi-linear. You can see here a of xy. Okay, that a is a function of not only x and y, u of xy. B again xy, b xy, u of xy. So that when that enters, okay, then with the C also, C can be xy and u of xy. So if the dependence of u xy enters for the A term, B term and C term, this is also PDE, but it is a quasi-linear. When you have this dependence of u of xy for the term A and a B and C, when it enters, it is a homogeneous, but it's a quasi-linear. It's not a complete linear equation. Okay, and this is when this is equal to 0, it is a homogeneous. When this is equal to 0 with this condition, you retain the same condition throughout. When it is not equal to 0, then it's going to be a non-homogeneous, but it is again a PDE is a quasi-linear, non-homogeneous when this is not equal to 0. PD is non-linear when it is not linear and not quasi-linear. So both the conditions will be violated. When this is violated, then it becomes a PDE non-linear. And I know that now this is one of the prime area in mathematics, applied mathematics, where the solutions for the nonlinear has been emerged. Very many new things that have been emerged by this studying this such terms. Okay, there are so many people are working on this PDE nonlinear. So these are the typical classification that you have. You have a homogeneous, non-homogeneous, quasi-linear, and under that you have a homogeneous and quasi-linear, non-homogeneous. Then when these both are not satisfying, not linear and not quasi-linear, then they become a non-linear PDE. Some of the typical examples of the PDEs are, you can see here, it's well known, we already exposed so much on this, which is a typical 1D wave equation. You have a U is a function of x and t. It is like x and y. Okay, but it's the second order. Okay, this is the second order. This 1D wave equation. And here you see there's a first order and there is a second order on the right hand side. This is 1D heat equation. It's also used for the diffusion purpose. Okay, diffusion study also similar equation. So this is the 1D wave equation. This is 1D heat equation or a diffusion equation. Again, this is Laplace in 2 dimension. Yes, 2-dimensional Laplace equation. You can see here dou square u by dou x square, dou square u by dou y square here. Okay. You can see this is also similar to this, but you don't have this constant square of the constant is missing here, and it is sum. Okay, this is the sum. But 2 variables are there. U of x comma y. This is equivalent to this u of x comma t. But this is a bit different from this one. This is 2D Laplace. And if you have on the right hand side some constant is there, like if not constant, it is of some function x is a function of x and y, then it is a 2D Poisson equation. And this is 2D wave equation. You have another term which is here. Add this, and you can add another term for the Laplacian. It becomes 3D. Similarly, you can have a 3D wave equation also. D square y by d z square. If you add, you become 3D. And every one of them are challenging. There are so many people are working on that to understand that so much has been emerged by analyzing these things. This is the combination of the second order, and there is a combination of the second order and the first order. And there are first order equations also. So these are some of the typical things which we have a little bit exposure. Particularly, I think there must be some knowledge about this diffusion equation and the wave equation you must have seen. Okay, so if you look at for a typical physical problem for ODE, okay, you can see this is an example for ordinary differential equation. You have a ball which is kept inside a hot water. Okay, it's a spherical ball, right? And this is the equation for the heat. Okay, you can see this rate of cooling. This is the time dependent of theta. It's a temperature. Okay, which is varying like this. This is the typical ordinary differential equation, first order differential equation. Here you have a ball which is kept in a hot water. and we would like to know what is really happening with respect to the temperature of this ball as a function of time. And this is what the basic equation is governed by the first order differential equation. And we can see the ball is a lump system. We assume that many things that has been assumed here. If you go to the next case, same thing. If I look at it and make a comparison, you will see the difference between this and this. So many assumption which goes into this, okay, which means bottom and the top is the same temperature. There is no conduction. It's not been considered. Convection is not there. Okay, there are many things that has been removed. They have not been have been assumed, and then this equation has been found. And with that assumption, whatever result that you are getting, you can analyze it. And then if you wanted to improve the system, then you have to look for the other additional terms or additional effects that are to be considered here. So this is assumption. Ball is a lump system. Many things has been put into the assumption, and then this has been arrived at. Look at the same thing. Okay, and you have a hot water here. Again, the same ball is here. It's a lump. It's not a lump system. It's a spherical ball. So now the T, how does it vary? It depends on the temperature variation of this ball. Is very much depends on the radius of the ball. Okay, then angular theta part. Okay, so now you can see number of independent variables. You can see the R, theta, and phi is also there. Plus you have a time variable. Same problem, but we are looking at in considering every aspects of independence. What happened with respect to the theta when you are moving a spherical? You keep it as a spherical geometry and look at it with respect to the radius, how the temperatures are distributed. That we can analyze it by considering the all the variables, and this become a partial differential equation. This become a typical PDE where R, theta, phi, and T should be considered. Then you describe the so-called the heat dynamics or the temperature of the system. How does it get distributed as a function of these parameters? Okay, so this is the one typical case where we come across this type of a behavior. This is what we call as a lump system. This is not lump. There are every aspect. Now we are trying to look at it. Okay, that's how it's being done. Well, so now.
So what is meant by lumped system?
Lump
Mean
system means you see the lumped means here we are not bothered about this radius of this sphere. First thing, we don't even bother about the spherical geometry. Okay, geometry has not been considered at all. Okay, we just taken it as a ball which is there, and its temperature is variation is controlled by this simple equation, assuming that all throughout the ball temperature is same, but that cannot be the true. Here and here it may be varying. Is that right? For a given radius of the ball, there is a hot water around, and if you look at the temperature distribution within this, okay, there may not be the same thing, and it may vary with the angle. Okay, and as a function of time, of course, this is no one variable is here. That one variable will be there. So it is R, theta, phi. All of them are missing here, and it depends on what is the type of a liquid which we are using it. Okay, that also is not been considered. So there are many factors which are assumed. Okay, and if you assume so many things, then we call it as a lump system. And if you don't assume, try to have every one of the terms into consideration and set the equation and try to look at the solution, then that will be completely different. Okay, so when you assume all possible what do you call the minimum things that can be taken into consideration to start with, then look for the solution. When you start do that, it is called the lump system, and you try to add every one of the contribution and try to elaborate in detailed way and try to look at the solution. Then it's going to be a not lump system. So this is what the meaning of this lumping, putting them together, all of them like this, and every individual contribution which we try to consider here. So what type of suppose if you say there is a ball Even it depends on what type of a fluid or a gas which you are going to fill it in. That also matters. So if you take gas into consideration, and then you can have a density and pressure, there are so many factors, even that those things are not been considered here. You get the point?
Yes, sir.
Everything matters now. What type of gas which you have, what is the pressure, what is the kind of a pressure? These are all has been now not been considered. Even this is not lumped me to greater extent, it has been other things have been considered. But again, that other parameters, if you modify, then that should also be contributing. So take everything into consideration, then look for the solutions. Okay, that's how one should try to improve your analysis of the results. So this is the starting point, and add one by one, and then try to look at the solutions. Okay, so now if you look at the classification of the second order linear PDEs, what are which we have mentioned, which is equal applicable for the homogeneous and non-homogeneous, quasi, and then nonlinear. That is also equal applicable here. In addition to that, second order linear PDEs are classified by looking at the terms that what you have here. For example, you have a second order derivative here. This is a second order. This is also second order, but you have a dou x and dou y, both are there. Okay. So if you look at the Laplace, this will be 0, b equal to 0. Okay, only you have a two-dimensional Laplace, means this and this will be there, d also 0. So this is the general term. In fact, some more terms also will be there. You will see that. I'll show you that what are the other terms that you have. But that doesn't matter. But what is the important thing which is going to be useful for classification is this ABC, which is important. It will decide you what will be the nature of the solution that is possible. We can see that A, B, C are functions of x and y. This is a function of xy. This is also a function of xy. This is also a function of y. This is, all the three are function of y. And D is a function of, see, x, y, u, dou u by dou x, dou u by dou y also. That's what the thing that you have. Okay, so now the deciding factors are based on this ABC for the classification. Okay, now this classification has been divided into three groups. Now, three of them are the elliptic, parabolic, and hyperbolic. Classification of the second order linear PDEs are classified elliptic, elliptic, parabolic, hyperbolic. What is this terminology which is used? Where do they come from? Do you have any idea about what could be the origin for this elliptic, parabolic, and hyperbolic? Any guess? Where do they come from? Okay, we'll see that. What is the origin for this? What could be the possible origin for classifying them? They have this type of an equation. It will fall into either elliptic or a parabolic or a hyperbolic. Okay, let us look at this well-known. You are familiar with the quadratic equation? Ax square plus bx plus c. This is a quadratic. But general quadratic equation is ax square plus 2 bxy plus cy square plus dx plus ey plus f. This is what you are general quadratic equation. You can see A, B, C, D, E, F. There are 3 plus 3, 6 constants are there. And you have a variable x square here, y square here. X, y is here, and x separately, y separately, f equal to 0. The discriminant, which is d square minus 4ac. d square minus 4ac. The solution will be an ellipse, hyperbola, or a parabola, depending on whether the discriminant is positive, negative, or 0. So there seems to be a bigger analogy between this and to this equation what you are looking for. Okay, I hope it is clear for you. Quadratic curves can be studied by using this. You have, this is well known for us. When you do that, when you might have done it in your basic classes, mathematics, you have an analytical geometry. The quadratic equation generally described based on this type of an equation. And what we come across is this a special type. Okay, ax square plus bx plus c. Okay, so now with this, you have a b square minus aac is there, and depending on this magnitude, it will be classified as ellipse, hyperbola, and parabola. And by the analogy here, you can see A, B, C, D, E, F. Similar to this. You have a x-axis second derivative, y second derivative. Xy again second derivative, but x and y class terms will be there. This is ux separately. This is uy and plus f. So there seems to be very close connection between these two. Okay, in that case, then b square minus ac, something going to be here, will also fall into this category of the ellipse, hyperbola and parabola. So now this equation, this quadratic equation, what we have, it will be an ellipse or a hyperbola and a parabola, depending on this b square minus ac. That kind of a features are here. Therefore, it has been classified under elliptic, parabola, and hyperbola. Nothing great here. And if you are familiar with this, then you would understand things. Okay. Now let us try to understand this so-called discriminant, which is b square minus 4ac. That I am going to calculate here. Okay. And I am making a contour plot of this. This contour will be either ellipse or a parabola and a hyperbola, depending on this b square minus ac. That's what this says. So I would like to know whether that's being classification will be available when I visually look at these equations. Correct? It should happen, no? Definitely it should happen. They say ellipse. What is the condition that is being used there? That should be satisfied. When it is satisfied, I should see the ellipse on this plot. Similarly, what are these conditions which is going to satisfy for the hyperbola? I should see the hyperbola. Similarly, parabola. Okay. So let's try to look at that. And before that, we just identify, for example, b square minus 4ac is less than 0, then the equation is elliptic. This is the term. B square minus 4ac is less than 0, then the equation is elliptic. Because I'm evaluating that also parallelly. Okay, b square minus 4ac. If it is a minus, which is less than 0, then I should get an ellipse. The contour must be ellipse with the condition that's equal to 0. Correct? It happen, no? Otherwise, this analogy may not be right. Okay, so let's try to look at that and try to have some understanding about this equation, how it's going to behave with these ABC parameters, and then try to understand, yes, things are seems right. This is now you even though there is ABC parameters are there, you don't see anything here. So this itself gives some clue for us. This is going to be region that also really matters now. Okay, so now you can see here what is going to happen. B square minus 4ac. I have not come to the minus. Is it not? If I come to the minus, okay, I am coming to the minus now, plus b square minus ac. Able to see that? It's an ellipse.
Oh, wonderful, sir. Wonderful.
It's an ellipse. You will get a feel. Yes, this is really true. As long as it's minus, you have an ellipse of various possibilities. And the D consequence is shifting. E consequence also shift. F is also changes the size of that. As F is a function of all of them, is it not? You have seen the D. This is how X, Y, U, dou U by dou X, dou U. No, everything is there. No, not everything is playing a role here. Okay, so now you can see, you will get a clear-cut picture about what is this elliptic part of it. Okay, I'm able to see and get a great feel about, yes, this is, whenever this condition is satisfied, I'm getting an ellipse. And this is with the satisfaction, F is equal to 0. But this may be satisfied with different values of right-hand side also. That has been shown here. I'm not making it equal to 0. 0 is a specific case, the general case. Is it not? You get the point? Several contours that are there, they are all similar. Okay, which is satisfying the right-hand side equals to different numbers. Understand?
Yes, sir. Yes, sir. Each circles are
Yeah, it corresponds to right-hand side in particular magnitude. So when you are talking about the equations here with respect to these, what is really matters now? What is the region you are looking at is? What is the boundary? And what is the initial condition? These two play a role, important role, is it not? Do you have any boundary now? There is a boundary for this. Okay. And similarly, you have a boundary here also, right? And initial condition also you need to have, because there is an initial condition requirement here. This is dou u by dou x. Okay, this is the second derivative. Then I need to have the first derivative of this x and first derivative of y. So initial conditions, boundary conditions, they are all going to play a major role in your PDE. So it is not like in the case of ODE where you are bothered about only the initial conditions. But here it's not only initial condition, boundary also matters. Because beyond certain region, you don't see anything. No contribution to these equations at all. So therefore, you have to really take care of this boundary conditions plus initial conditions and then look for the solutions. So regions are really matters. Okay, you can see. So if this doesn't mean that it's not an ellipse. It is an ellipse only a part of thing is been seen. Okay, I'm able to push it in by changing the other parameters. Okay. So therefore, this every parameters their coordinates values. Now this is x and y now. So ABC also a function of x and y now. You understand what I'm trying to say? This A
Yes, sir.
is a function of x and y, correct? Okay.
Sir, they are merely numbers, A, B, C.
But it is in turn connected to this. When you take a derivative of that, it's going to be matters. It's not just mere constants. It is going to be a function of x and y. See, now I change it. Okay. Are they not affected? X, all the x and the y is affected, na?
Yeah.
So which means A is also a function of x and y. Is influencing, is it not? Every one of the data points being influenced by A. Correct? Which in turn
Yes, sir.
implies
Yes,
here
sir.
appears to be a constant. And not only here it is going to be a which is in function of x and y explicitly seen, because it is the region in which we are having a derivatives, first order derivative and second order derivative, and which you are going to look at the parameters which is also a very much depends on the value of the x and y. That is what the thing that is emerges now clearly. Okay, you can see here. So it appears to be a constant, but for any minute change of that, your x and y coordinates completely change. Right? Okay. See, now the whole coordinates has been shifted, no? Size has been changed. Therefore, all interdependence is there. And what really matters is with all these interdependent magnitudes, what could be the region that can cover, what could be the initial condition that's required, that should also be put into this, and then look for the solutions when you make this analysis. So now, if b square minus 4ac is less than 0, then I have a elliptic type of a curve. That is what will be the results that you have. Therefore, it is being classified as elliptic. The first case where you have t square minus 4 is less than 0, then the equation is elliptic. For example, I think typical cases is one example has been given. Example, dou square t by dou x square, dou square t by dou y square is equal to 0. This b equal to 0. Okay, this is the Laplacian. Okay, two-dimensional Laplacian. A equal to 1, c equal to 1. Okay, minus 4. This is an elliptic. Correct? You agree with me? So this is what the feature that we are looking at. Temperature variation on the xy plane. This equation says about that. It speaks about that t as a function of xy. How does it vary? With an initial condition, I'm whether I'm going to heating at this portion or heating at the center of this or heating at this region, and then how the heat is going to move. Okay, how the heat is going to move, how the heat is going to be changing. So I have several options. Or I can have one line of that and take it and then try to heat it at the center and look for what is really happening within the one-dimensional case. This is the two-dimensional case x and y. And how the heat is going to be distributed. Okay. So there are so many types of possible conditions that are imposed on that, and then look for the solutions and understand about the system. And they provide lot and lot of information about this heat dynamics. Okay, it's possible to see how the temperature is getting distributed in X and Y and Z planes with the various conditions. But most of them will be, you can see this term will not be there. But you may ask what happens, sir, if I include this? Well, you are going to see this quasi type or it's going to be a nonlinear type. Okay. Then you look at the solutions and then justify what is the contribution of this, where does it come from, and what is its influence on this. All this can be studied. Okay. So therefore, that's what the first part, what we have, first classification, which is by looking at this analogy, we could be able to feel elliptic. So which means immediately elliptic. If you say elliptic, immediately what you have to come to your mind is that b square minus 4ac must be less than 0. Which means that magnitude must be negative. That is what your first check that should be done. Okay, that's the first part of it. Second is there is a discriminant which can be 0. Can I make it 0 here somewhere? Is it possible to make 0 here? With this, is it possible to write a 0 here? No? I'll make it this is 2. B square is 2, which means B square is 4. B is 2, B square is 4. Then what you have to do? Minus 4AC. What do I supposed to do? So my thing must be 1, and I make this A is also 1. Am I right? Okay.
Yes, sir.
Now you can see what is happening. Okay. So when you say this condition equal to 0, you can see here parabolic. It's a parabola. It's a parabola. Okay. You should be very careful about getting these conditions and should be. So what is the next possibility? I can have this is 0. You can have it. Is this a parabola? Look at it. Is it parabola? It's not parabola because this
Yes,
is
hyperbola.
that's hyperbola. So this 4 should be eliminated. So minus 4 AC. That will be possible by having it. How do I make it? That it should become 0. So this is 0. I wanted to have one more condition possibility to show that b square equal to 4 minus AC, which means how much I should, can I have this? A C, this is equal to 1. Might be possible to see that. Okay. What happened to this? This is minus 12 now. That's not of interest to us. But I wanted to have a 0 here. I'm coming close to 0 somewhere. 4, minus 4. Okay, you can make it 0 somewhere. Then when you
B can be 2 and A and C are 1.
A and C are 1. That's what I have shown you previously. Okay. This is what I have shown, but I am looking for one more condition where b square minus 4ac should be 0. Well, there is a possibility. Probably I can have this is minus 2 b square. Okay, so 4. Okay. Then minus 1. Okay. Again minus 1. What happened now? Now 0. Is it 0? No, it's 0. Okay, similar condition. Because A minus, minus and minus again, because there is already minus sign. This product become a plus. So minus b square is equal to 4. Then minus that's equal to 0. So this is also satisfied here. Then you can see this is going to be a parabola. Correct? Is it right?
Yes, sir.
It's right. So it's satisfied. That's fine. Okay. So now we have seen that less than 0 one case, which is an ellipse, and then you have this another contour. What you have here, there are two types we have shown, which is a parabola. And ellipse is something like, well, you have come to the positive one. This is an ellipse. I'm sorry, hyperbola. Okay, whenever you are in the positive region, it's a hyperbola. And when you are going to negative here, it is part of the ellipse. Please remember that this is part of the ellipse. Okay. Maybe I have to expand the scale now. It is a part of the ellipse. This is minus. Okay. So therefore, you should be careful about this analysis. Now we can clear elliptic, parabolic, hyperbolic. It very much depends on this experiment. What you have is similar to what you have in the partial differential equation. Corresponding classification has been brought in. But of course, these are all earlier stage. Now there are so much development that took place after these nonlinears and quasi-linears. So there are under each category there are several subgroups that have come. So those things cannot be categorized like this. Okay, they're all depends on the cross terms plus fire terms of the first order. All are influencing. Okay. So I think this classification now you can please remember through this quadratic equation through this, and you can see here another condition. This is my positive, a negative value. If you go to positive, you can see here other say okay. This must be, what is this equation? This must be hyperbola. Okay.
Yeah, hyperbola.
All hyperbolas. Beautifully it has come now. You can clearly see that. And specific case where we have seen these two now, well, 2, and this is equal to 1, and this is again 1. What is it? We wanted to have it 1, 0. Yes. This is when it is 0. So you have a parabolas. Okay.
Yeah, yes, sir. Yes, sir.
It's so clear. It's so clear that you can feel it that this is what really happening with respect to these parameters. Now, what is important here when you are looking at the partial differential equations, regions really matters. Initial conditions also matters. Initial conditions, there is a possibility if there are second order means initial condition for every variable you need two initial conditions. Okay, for every independent variable, the two initial conditions you require. If there is a boundary which is involved, then the boundary condition, if you incorporate, you have one type of a solution. If you don't incorporate that, you have a different kind of a solution. So that also, for example, you have a water wave. Fix the region. Okay, give the proper initial conditions. Wave travels and goes and sees that when it's coming back, the wave which started from the beginning and the reflected one, they try to interfere each other. So interference pattern will be seen if you don't incorporate the boundary conditions. If you incorporate the boundary conditions, then you can eliminate that interference pattern. See, you understand what I'm trying to explain? You have a water wave which goes and it is confined to a region. Okay? There is a boundary which is involved. If you don't incorporate the boundary condition, it goes and comes back. When it is coming back, the one which is going from center, they try to interfere, the interference pattern can be seen. But if I incorporate the proper boundary condition there, Okay, then you have a completely different result. It depends on what type of boundary condition you are going to use. Correspondingly, your results will change. So this type of things one can really do it and generate them, visualize it, and feel more and more about this waves in 2 dimensions and then waves in 3 dimensions. Heat equations, then you have a diffusion equations, the transport equations. There are so many types of equations that are available in PDE, and every one of them are really challenging, and it gives a lot of input to understand about the physical systems. So you can really feel that these much powerful things that are available in terms of PDE. And if you are strong in PDE with the physical background, then you are really mastered in your physical problems. That's what really happened in quantum mechanics. Time dependent, okay, which is first order, and you have a second order in the space, which is similar to your diffusion equation. But what happens? The time dependence in the first variable, it's a complex space. So that makes all the difference. 1 minute. மீட்டிங்ல இருக்கிறேன் பேசாம நில நில ஓகே. Okay. Is it audible for you?
Yes, sir. Yes, sir.
That's fine. Okay, so I think I'm trying to explain this water waves. Okay, it is not only the initial condition that matters. If you wanted to take the boundary effect also, that should also be considered properly given the boundary conditions. Right. So now we have the parabolic is this, and this is a typical example here. You can see here as part of the 0. You can see here A equal to K, B equal to 0, C equal to 0, D equal to -1, which leads to 0. And this is your typical, what you call this heat equation, which is again similar to your diffusion equation. Okay, so hyperbola is greater than 0. Of course, B square minus 4AC is this, and then you have the other contribution. This is the typical waves. Okay, wave equation here, which is greater than 0. So therefore, you have the so-called the hyperbolic solution type is hyperbolic type. Okay, I believe that the classification is made it clear for you people, and I hope there should not be any fear to say whether the given equation is going to be of hyperbolic or parabolic or elliptic, at least for the classical type of classical PDE equations. Okay, fine. I hope this is clear for you for an introduction to this PDE equations, the classification. So let us look at this so-called transport equation. Okay, this is first order in time and first order in space, and sum must be equal to 0. This is the transport equation. So now we can see this is the first order in, this is nothing but dou U by dou T. I have written here. Okay, and this is dou U by dou X, which can also be, for your clarity, what I refer dou is, you take this one, I am writing this differential with respect to T plus differential. That's what the meaning of what I have written there. T comma X. Okay, you can see here differentiating with respect to time, differentiating with respect to the coordinate system X. See what I have here written here. Second variable U of 0, 1. That's what your output says. Then first variable U of 1 comma 0 X of T. So when you write like this also, it means It is dou u by dou t. This is dou u by dou x. That can also be written dou with a suffix, which you can write it by use escape, pd, again press escape. Then afterwards, you put control underscore, then add this suffix. That's all. Then afterwards, your variable. That's what you should do. But once you know that how to do this one, then you can automatically do the other one, because you can easily just, it can be copied and taken it there, and then put the plus, put over here and change the suffix alone. That's all power. So this must be x. And if you wanted to have a double derivative, what you have to do is just see what's happening here. I am taking this.
So you put it as yes, partial
Yeah,
s.
yeah, that's right. That's right. This must be x. So double derivative means this is what I have to do with respect to x, with respect to the, this is the second derivative. Okay. Enter. See? 0, 1 by 2. Twice you have done it. This is x written twice. That can also be done here by having this and this. What happened? I don't know. Let me try here. I think I should add a comma here. Should be R. Yes. Don't miss the comma. You get it now? What I have here, I'm getting it here. So when you are taking a second time, should have. If you have a cross term, dou square u by dou x and dou I, if you have, then what you have to do? Copy this, paste, plus add this. I have a t. Okay. Now I just. Okay, you get it now? This is the second derivative with respect to the position, second derivative with respect to the time. This is with respect to the first derivative with respect dou u by dou x once and dou u by dou t also, which we call it as a dou square, but the denominator will have a dx, dou x and dou t. That is clearly indicated by having 1 comma 1. That is the cross term that you have with respect to this. This is nothing but your dou square. Yeah, I'll just write here. It should be written as probably like this. You have to write differentiate with respect to the x and the t, and you find this must be added here. So once you this clear to you, then everything is clear. Now d of x comma t. Maybe this should not be here. Probably that should be taken here. Yes. Okay. You can see here 1 comma 1. This is correspond to this. This is second derivative with respect to this x, second derivative with respect to the t. This is first derivative x and first derivative t. That is what your u of 1 comma 1. This is how the partial differential equations can be handled in the Mathematica. Not a difficult thing at all. Okay, is it clear?
Yes, sir.
Okay, now we have, what does it mean? Now I have first order in time, first order in position, that's equal to 0. This is what you are actually equating. What is the solution will look like? What is u of x of t? Okay. It's a very interesting situation now. You get the point what I'm trying to say? What could be the solution to this equation? Well, we try to look at the solution now. One possibility is that I have written as a transport equation. Transport means something should be transported, no? either in terms of a density or a mass or heat. Something should be transported, is it not? So it should. In fact, you know that uh, traffic flow, traffics, vehicles are moving in the roads. You must have seen, no? One point it
Yeah, yeah.
one point it starts or enters, and another point it leaves. Okay, there's a position, there is a time dependence. It is something like a flux, which is entering at a point and leaving at another point. Okay, if you integrate over time, you'll get the total number of vehicles that is crossed. Okay, and if you put it from one point to another point and then look at in terms of the flux, what is the flux that is entering and leaving, what is the net flux, and then you can find out at a given time how many vehicles that are crossing. Okay, that's also possible to study. So there are many issues that can be understandable through these equations. Only thing, you should know what is the kind of a condition that you are going to impose here. What condition? Suppose if I write u of x comma 0 is e power minus x square, which is the initial condition for this. Okay, I can have anything. I can have a sin x, cos x, tan x. You can write it anything which you like. The next variable which should be there. With that, if you try to look for a solution, the solution will be function of replace this variable with that function with x minus t. Okay, e power minus of minus x minus t. Okay, let's see that's what's happening now. You have this simple equation here, which is equal to 0, which we have made it, and d solve, which we have used now, and it gives a t1 is function of t minus x. It's not a constant. T1 can be anything, any function. Can be function of. Now in this case happens to be exponential. E power and c minus of t plus x whole square. We'll try to do this first and then we change this to something else and then look for it. Okay, what is happening? So you make all possible changes and then look for it. Correspondingly, it goes into that. And will that be satisfying this equation or not? And one more thing also we try to look at is, you know what is the meaning of a derivative of a given function, right? What is the derivative of a given function? It's going to be a scalar quantity or a vector quantity. U of xt is a scalar. And when you take a derivative of that, it can become a vector also. It can become vector quantity. So that's also possible. And you can see the directional derivative here that enters through this so-called transport equation or the partial differential equation of first order, in which you have the two variables are there, corresponding first order variables. Both have been considered. When that's equal to 0, that's going to be a transport equation, which is what the meaning that you want to convey here. Let's try to see this. Let's assume that this is right. C1, I can have a sine, cos, tan hx, cot hx, logarithmic of t minus x, anything that's possible that will be satisfying. Okay, so for the time being, we'll assume that this is right, with the e power minus x square as a u of x comma 0. For the time t equal to 0, I have this. As time goes on, what happened to this equation? That's what we are interested to look at. Okay. In fact, you can understand more about that through this equation also. This all. This is done now. 10. No. This is done. Okay, that doesn't matter. This is what really matters now. It should be this. Then with this solution of e power minus x square for the initial condition x of 0, e power minus x square, this is what the result that I have. But I'm going to evaluate and see what's happening with respect to the time. It should going to evolve or not. And also you can check whether it's going to satisfy this equation. This equation, where is the transport equation? That will become 0. And it must be true for any of this function which you are going to do, that should satisfy. Okay, let's try to have this an x v square e power of my expert type behavior is like a Gaussian derived function, and this Gaussian is consistently moving with respect to the time variable. Okay, let's see. This is what the solution is. So, what is that happening? As per a different time, it's getting moved, but nothing happens to this magnitudes at every time, only shifted. That's all. Okay, so let's try to have some more understanding of this equation for that, right? By putting it in this form. As a function of t, if I evaluate this, for example, I'm going steps of 0.5. There are 6, 1, 2, 3, 4, 5, 6, 7 of them. Of course, 0 will be there. 7 intervals starting from 0, time t equal to 0, then 0.5, 0.6, sorry, 0.5, 1, 1.5, 2, 2.5, 3. Like that it goes on. 0, this is 0.5, 1, 1.5, 2, 2.5, 3. This is the curve. You can see the peak will be maintained. Only the respect to time there is going to shift. Is that right? The features are right?
Yes, sir.
So that's what this shown here in the two-dimensional plot. Okay, for every t it's getting shifted. That I'm just showing it. So this as a three-dimensional picture as a function of time is getting, same thing is getting transported to somewhere else, somewhere else, somewhere else, somewhere else, somewhere else, somewhere else. Is that right? It's the beauty of this function. Now, let us put some questions on this. Now, okay, so you can see that x is one axis, t is on the another axis. Okay, this is t axis, and this is your x axis. Correct? This is x, and this is t. This is at the third second. Correct? This is 0 second, 0.5. This is 1, 1.5, 2, 2.5, 3. And this peak position gets shifted uniformly, and every data point correspondingly gets shifted. Okay. Now, this y-axis is u of x t. Am I right? I'm sorry, z-axis. This axis, what we have up to 1, from 0 to 1 magnitude is u of xt. Agree with me? This is my x-axis, this is my time axis. Then x and t curve, this is the magnitude. Is it not? U of xt is this curve, these points. These are the z-axis is u of x comma t, because this is x, this is t. Which means I can have a curve for a 0 time, all x has been plotted here. 0.5, all x has been taken, starting from -4 to 8. Like that, when I do it, the peaks are getting shifted by the 1 unit of that, it has been displaced to this. 2 unit of time here, 3 unit of time here. This is 0.5 unit of time. Okay, this is 0.5. From here to here, 1 unit. If it is moving with the velocity of v, then this is the displacement of this respect to this. Okay, now if I look at this u of xt vertically, you see at 0.5 point, whatever you have, all of them will have a u of xt is constant value. Agree with me? These data points, 0.5, every time interval, okay, go and return back. You are going. They're all constant values. Are they varying? Hello.
Sir, we didn't understand what you
That's
mean.
right. Okay, okay. So u of xt is the z-axis.
Yeah.
Right?
Yes, sir. Yes, sir.
Okay. It has some magnitude, now it is varying.
Yes, sir.
Fine. Now take any position and any interval of time. Okay, fix one position on time. For example, in this curve, whatever you have, say 0.5. Okay, for example, 0 position, right? 0.5 second. What is the magnitude of Vx of t? Is same as at 1 second and 0 position. Am I right?
Yeah.
Agree? This is important. Very, very conceptually, it's very, very important for you. U of xt for a given position and given time, they are always constant throughout. Am I right?
Yeah, you can take a different x, but pairing must be properly be taken to make the
That's
value.
right. That's see, you take this point, okay? The first curve. Take the 0, instead of 0, you take a, say, let me take 0.5 is the distance now. 0.5 meter, let me take, right?
Yes, sir.
Okay, time is 0 second.
Yeah.
I'll come to this. Same 0.5, okay?
Yeah.
This 0.5 is, and this time also 0.5. There is another point, I'll get it. This magnitude and this magnitude is same. Go to the next one. What I'm referring is that u of xt for this curve for x equal to 0.5, t equal to 0 is same as x is equal to 0.5, t equal to 0.5, x is equal to 0, okay, t equal to 1, that also same. 1.5, that's also same for the same point of x. This height is going to be consistently same. Even though it gets shifted, but the height is same. Am I right? If I draw a line connecting them, there's going to be a line which is slanting line that will be there, but the height of that line from this bottom is same magnitude throughout when you are moving along this curve, but it may have a finite slope. Am I right? No.
Sir, basically you are for getting the let us consider the peakest point, peak
Right.
point.
At zero
Now,
time,
yeah.
at zero
Then
distance, okay?
yeah, yeah.
Every time, like if I connect them, there is going to be a
But
line,
the
no?
second curve, the x would be slightly shifted,
Yes. But the magnitude of
and
u of xt is same throughout.
yeah, yeah. That is right. Okay.
That is the point.
Shifting. Okay.
There is a shifting, but the magnitude of every shifting is same. That's what your u of xt is along this axis for a given position and time. If you are moving along this, so the so-called distant wise, see, you can see this point and this point, they are not the zero.
Yeah.
You get the point?
They are yeah, but
Okay,
they
but the
by
height,
doing some
is same, no?
yeah,
Throughout.
height is same. Yeah.
Similarly, come to the third point or a fourth data point. That's also true.
Yes, sir.
Ah, that's the
That
beauty here.
means they can be
Ah,
superimposed by doing some
it is,
linear.
yeah, it is right. Now, what you are having a, so I have a lines now, okay? These lines are having a constant u of x comma t. That equation I can form now. That equation of a straight line, can I form it now? Because the straight line, they are not, they will be always displaced with respect to each data point. They are making an angle, is it not? Slopes are different.
Yes, sir.
What I'm referring is a line which is drawn with the same height with respect to the z-axis. Okay, connecting all the points. That line has a constant magnitude. Okay, is that right? Constant magnitude with the u of xt is same. That's what I'm trying to say.
Yes, sir.
Agree?
Yes, sir.
That's fine. So once you have that, then that will give a lot of information about the system now, which means u of xt, which you are formed by a straight line that's going to be a constant. When I take a derivative of this equation of a straight line, I have this so-called the transport equation. Get it now? So I have an equation u of xt on the right hand side with the variable x, okay, and it's going to be c and t. Then you can try to, so it is sort of a directional derivative that you am getting it every time. Okay, my lines are directional derivative for the u of xt. You get the point? Because these are the lines for every same height from the bottom. If I draw a line, okay, I'm going to get a straight line which is making a particular angle. They are not going to be parallel ones, but you would see that there's going to be a lines which has a different kind of a constant magnitude that you will get it. That's u of xt. U of xt is constant for those lines. Then if you take a derivative, then it's a directional derivative that if I combine here, you will end up with this equation. To confirm that, what you can do, you take this equation, find the derivative with respect to the position and time, add them, that goes to 0. That's satisfied. Get it now?
Yes, sir.
I just put it over here again, whether it's going to be true or not. So the x plus, okay, I just check it here because u of xt must be this is the solution that you have. That should go here for differentiating it and just calculate it for both. This is what my u of xt here. This is what your one is differentiated with respect to the position, other one differentiated with respect to the time that goes to 0. Okay. If you can put it in terms of a directional derivative and it's possible for us to check that, that's also will satisfy. Okay. This the line which you are going to draw along this xy plane or along this you are on the line. This will be on this above this plane, various heights along the z-axis. You draw that they are all directional derivative of this u of xt. That's going to be a constant, and that constants can be used. That constant you can also prove that this is satisfying. So this is a directional derivative component of this equation, which is the transport equation. This is something is being transported from one point to the other point for a particular direction that has been observed through this equation. Okay, so this is what the meaning of that. And when it comes to the quantum system, what happens? Quantum system. What will happen to this same Gaussian function when you do this time evolution? Space and time evolution. This will be true, shift will be there, but during the shift, what happens? Spread will be more, correct?
Ah, okay. Yeah.
Height will be decreasing.
Yes, sir.
So transport in the quantum situation is completely different, correct?
Yes, sir. Yes, sir.
So this height will be decreasing, full width half maximum also getting increased. and after a certain time, it will almost get dissipated. Okay, so you see, evolution of the free wave packet will be completely different from what is that you are looking. That's also Gaussian only, but you will have some denominator terms that will be spreading it out with respect to the time. Therefore, the peak also will reduce and spreading also get enhances. That is what happening when you go for a so-called the quantum regime. The particle distribution or the transport will be of that kind of a thing that's going to happen. It's completely different, but that is also Gaussian. This is a Gaussian. This is also Gaussian. Correct? And please remember that when you do it in a real space, okay, you have Gaussian, momentum space also Gaussian, but what is the difference is the denominator term will be multiplied in one case. In another case, the same factor will go and sit in the denominator, it will be divided. So one fellow shrinks, other fellow broadens. This will be half maximum. So that is where the uncertainty enters. You get the point? If I have a denominator factor, if I have some factor in the numerator, when I take a momentum space, that factor will go to the denominator, which will spread. When it is other case, it's going to be shrinkage. So you can see del x del t will be varying, and del x del t also function of time. There are many interesting things that evolves when you try to understand that so-called the evolution of the wave packet, where it is a time dependent and a position dependent, but there is a completely different kind of a mechanism that goes and different kind of an interpretation that is given. So therefore, the Gaussian will be very, very important function to understand. That has an important role. In fact, harmonic oscillator, quantum harmonic oscillator, second case, which I have dealt it, and the ground state is Gaussian. You can see here, it is a Gaussian. Correct?
Yes, sir.
Half h grams omega, it is a Gaussian. It is a Gaussian type wave function. It is normalized. And you see, when you understand this PDE and looking for the solution in terms of a, these are eigensystem. This is an eigensystem now. Okay, one line you have an answer. See, beauty of it. You get the point? It's an eigenvalue system. Am I right?
Yes, sir.
I am having just this equation to solve for 1, 2, 3, 4 eigenvalues and eigenfunctions correspondingly. It has been calculated and is given for this quantum harmonic oscillator energy system. Fantastic. See? Same thing if you try with this differential equation, you have to write number of steps and then you have to finally arrive.
Yeah. Yes, sir. Yes.
I'm just getting it with one line of right QHO, what is this derivative component, and then you thread it with this exponential. This exponential term, nothing happens, no, the time dependent. I'm threading it along with this stationary solution with the time solution. You can see here. This is the term which is added, multiplied with along with that solutions. Okay, thread with that, and I have this result, which is the full solution. If I add them, that's going to be a superposition, and fantastically one can see how this time evolution of the quantum harmonic oscillator takes place. Let's try to look at this. Okay, this is QHO. This is the eigenvalues, eigenfunction. I'm threaded with that. Find the charge density by taking the complex conjugate of that and fit some numbers. What are the units which you want? Whatever the atomic system of units which you want to use, you can use it. You see that number so that you can see the pictures clearly. And this is what your evolution of this wave package, or this superposition of the wave and its evolution of the time. So beautifully one can see. Amazing.
Sir, they were a very great mathematician. Thought of they think physical problems.
Yes. That is where, see. So now, if you look at PD, there are people, they work only on a one particular type of a PD. They exhaust all possible conditions and understand the system and mathematics as much as possible. Plus, they look for a physical system where this kind of equations can be applied and extract the information. Look at this time evolution of the four state, which is the sum of this all the four. Okay, that's also solution to the differential equation. That's kind of harmonic oscillator equation. Time dependent. Please note this is the time dependent Schrodinger equation. Get the point? X and t both are there. X and t, X and t. The whole thing has been arrived with the two equations, three equations. We are able to animate and see this. Okay. Superb. And see how powerful is this. And software is also powerful, plus ideas also great, very great ideas. D eigen system enough. If you want, you can put 8. Okay, you can get 8 also. It's a question of time. It will take. Okay. You have to wait for it. It's done. Already done. Okay. And get all of them. It's already done. Now you plot it. So I start with that. Okay, and look at the evolution of that. Still, it is going on now. I can start it and then look for the next result. Takes quite a bit of time because there are 8 such things and everything should be added up and then complex conjugate should be taken and then it is done. Already it is done. Okay. You can see here. Probably I have to change the range, plot range. Probably I can have it 0.3. Then check it. Yes. Now we can look at this. That's greatness. Okay. So this is the superposition of the 8 such waves. That's also solution to this equation. Time dependent Schrodinger equation, in fact. It's a solution to the time dependent Schrodinger equation. And its evolution, complete evolution can be seen. So now this is most important thing for us to understand. These eigensystem. We have seen eigensystem earlier, that eigenvalue, eigenequation, eigensystem is giving an eigenvalue and eigenvectors. Differential equations, there are eigenvalue problems that is being solved like this. The D eigensystem, it has been given here, and one can go there and look at this equation and see the number of applications with all possible differential solutions, differential PDE solutions. You can really enjoy them. You can understand so much about this 1D, 2D, 3D problems. Options are given, assumption, what are the things that's possible. Okay, heat equations, wave equation, Laplacian, and in fact, the similar equation is given here. Okay, numbers are there. This also has been plotted. Okay, this is same thing what I have shown, but I have shown it under 8 such things. Then some of the important properties, and then you look at the possible issues. So this is, I felt this is something which I wanted to expose to you, that see how great is this PD is, and then Mathematica so comfortably it handles. I know because when I was trying to do it with the Fortran to Mathematica differential equations, ordinary differential equations, separation of variables, and then combining with this time dependent, it took me so much of lines, so much of things to write. And here, after going through this, I felt it is just nothing to get Just like that, you can get the eigenvalue, eigenfunctions. Then they can be combined and then taken the complex conjugate of that, plot them, and look at the result. Okay. So now it's only one u of y by x equal to 0. There is a equation solution is given. Because when you try to look at such problems, your depth of understanding of your ODE becomes very, very clear. Because it's a combination of ODE, multiple variables, sort of separating the variables finally, and we will try to look for the solutions. Look at the solutions here. U of y by x comma y equal to 0. This is the region xy belongs to R square region. The two variables are there. Now, these solutions, when you look at it, you will understand that solution is, you can see there are ax and bx two arbitrary function. The ax is multiplied by y, bx is not multiplied with anything else, separately it is there. Okay, that's how it's there. And you have to really go deeper and deeper and try to understand what is that we are trying to do or looking for the solution. It appears to be too difficult, but when you have a clear-cut picture about like what I have shown from starting from the beginning, the classification onwards, you look at things carefully, then it will be easy. For example, you look at this one. This given equation simply means that u of y x comma y does not depend on y. This looks very strange, but it's nothing great here. Because the first derivative with respect to y does not depend on y, only can give this 0 when you go for the second derivative of y. Correct? You have to think it over that. Then understand this. Put it as an ax. Then now do one more integration. You'll get this result. Fantastic equations. They do great jobs afterwards when you come across such kind of equation. Okay? You understand what I'm trying to say? This given equation simply means that u of y x comma y does not depend on y. Then only this is possible. Then other things automatically fall in. You can follow that. So you write it as the u of y x comma y equal to a of x. Is not that. Where a of x is an arbitrary function. Integrating the last equation with respect to y, keeping x as a constant, it follows that the general solution is given by this. Okay, so this is what the solution that you have where ix, bx are arbitrary functions. That can also be obtained by c1 of x, c2 of x here by directly solving the d solve, which gives where c1, see y into c2x. This is the first term is here, second term is here. Get the point? Then C1, C2 are the arbitrary functions of x. Two arbitrary function which is a function of x. Two arbitrary function is a function of x. That's what the result that you have. Okay, another thing. So that the function, this xy not equal to 0, z not equal to 0 is a solution to the differential equation u xx, u y by u, which means second derivative of all. Okay, this is like a Poisson equation solution. Belongs to R3. This is not equal to 0. That's what it means. Now, take this, substitute, simplify. Further, find out uxx, uy. Similarly, uz gets. Combine them. You'll get a solution which is satisfying. Which can be shown here. D of x comma 1, xy comma 1, z comma 1. This is what the result. Then take this and find out one more derivative and add them, simplify. You'll get this result which is satisfying this equation. And you will understand more about this, how to handle such functions and how to get these expressions or how to handle through the Mathematica. You will understand more about the system. And this is going to be, this is what is this equation now?
Second order homogeneous.
That's right, but you have a xx, y, Laplace equation in 3 dimension.
Yeah, yes, sir.
Laplace equation in 3 dimension. This is satisfied by this. This is the solution to this. And depending on the initial conditions and the boundary conditions, number of possible solutions that are available. Okay, that's what meaning of it. This is one of the solutions. Similarly here, find the general solution u equal to u of x comma y of the equation. U of x y, you can see this is dou square by dou x dou y plus ux equal to 0. You follow what I'm saying today? This is dou square u by dou x dou y plus dou u by dou x equal to 0. You see how this is being solved. Look at the equations. And this equation consists of two different functions. Two arbitrary functions along with e power minus y. The previous case, two arbitrary functions with x with respect to x here. But here, since you have the cross terms, you find that cross term effect can be seen e power minus y f of x and g of x, two arbitrary functions. You can select some of the functions arbitrarily and make sure that this is being satisfied here. I think I have done some of the problems, which you maybe I can show it now somewhere. It must be available. The equation. Hopefully, I will have it. Yes, this is what I believe. Yes, not this one. One more. Yeah, dou square u by dou x dou y equal to minus dou u by dou x. This is the equation. Correct, now? Am I right?
Yes, sir.
For the equation which I have, this is method of solution has been explained here, and you can have a combination here. F of x and g of y, cos x y square, log x tan y square, x cube plus 3x plus 1 by of cot of ln of x, g of y equal to y square e power minus y. You just check it now, substitute them. See?
How many solutions are possible?
Okay, there are so many solutions that are given, and all of them are satisfying. Okay? So now you can see the complete difference between the ODE and PDE. And you have this kind of situation when I come across, there are so many possibilities that are there. So all the possibilities that one can explore them, try to see whether this is applicable somewhere where you can extract more information about the systems. Okay, so that's what the thing that's going to happen. So it's clear here. I just shown here 3 of them. Method of evaluation has been given. Get the solution, which already I have given in a printed form, which is actually handwritten form also available. Then u1 of x is f of x g over y cos x y square. This is what? u2 is log x gy is equal to tan y square. Here again, f of x gy is x cube plus x tan, which is 1 by f cot tan of log x, gy is y square e power y power 4. Exponential y power 4. Substitute x and y satisfy true. And not only that, you can have a linear combination of this that will also satisfy that equation. So whenever you have the equation of this type, this linear combination will satisfy, and similar kind of thing that happens here also. This is 2D Laplace. Okay. This is also solution. This is also solution. This is also solution. Then you try to check whether they are all satisfying. It is satisfying. And take a linear combinations. That's a fundamental theorem where you have the solutions of the Laplacian type and you have. You can always make a linear combination of them, add all of them and put it over there. See, U4, which is a sum of all the 3. That is also satisfying. So, you can see that's linear combination also works out so nicely. Then that's the condition where it is satisfying this kind of an equation. Okay. So, this is what the thing that happens with respect to this PDE of different types. You can try here also, which I have already shown to you. A typical heat equation, which is first order in time and second order in position. And if same thing, if I have a complex on this time and then try to look at in terms of the operators with a differential equation that's become a quantum mechanical problem, which is base of the quantum mechanics, where you have this kind of a similar situation, but the solutions are completely different depending on this the so-called the Hamiltonian. Things will be different. So now this as it is, this is what the equation that you have, which is dou u by dou t. This is dou square u divided by dou x square. That's what this here. Now you can put some initial condition properly. U of t 0. Okay. T is the first variable. I'm writing as a sine t. At time t equal to 0, or at time the position x equal to 0, this is the type of variation of the heat that is there. As the time progress, okay, what happened to the heat, the system? Okay, initially this is what this heat structure at time t equal to 0. As time goes on, this is what is going to happen. That's what the meaning of this is. Your u of t comma x is capital T. Capital T is a temperature as a function of time and position. This is what the result that you have. Initially,
Sir, we keep two sources like.
You can do very many possible initial conditions are there for this heat equation.
In this case, two peaks are the height. That
Yeah,
means,
two peaks are the height. Yeah, that makes the difference. You can have a
two
pulse like.
sources.
Yes, pulse also it's part. You just heat it at the center, no? Okay, maximum. Heat it and
Yeah.
leave it. And what happened as a function of time? I think that's probably available in the next case somewhere I have given. It's here. See? This is what the result that you have.
Yes, sir.
It at the center, and then it started moving it, and the where you will see the Fourier series will be there. Fourier series sum will be there. That will give, and the number of terms goes up. It will become much sharper, and this is blunt, little blunt. You can see here, and this is how the temperature distribution will be, and your conditions will be different now. Okay. So depending on the initial condition, things will change, and correspondingly you can have the equation. So this is 50 terms if I take, this is going to be blunt now, and it will become much sharper if you go for 100 terms. This is 100 terms now. 100, this is 100, not 50. You see here, this is 100 terms of this. So this has been considered, and then we made a plot of. So that will be of quite interest for understanding the heat equation, which is similar to diffusion. This is nothing but heat diffusion within the medium. Okay. So now you have 1D wave has been. Okay, this is being done. Numerical also can be done. Whatever which I have given here, no, this analytical solutions can be done numerically by putting it with the initial conditions properly. Then interpolation available and make a plot. You will get exactly same plot. Okay, so if you are not small, you can make a plot. The solution can be plotted and then check. You are able to reproduce the same results with the solution what you have found. Here also it's in fact it's interpolation. That is what is plotted. Okay. So now you look at the wave equation. This double derivative in time and double derivative in position, and you can have initial conditions of u of x comma 0 is phi of x, and u t of x comma 0 equals phi of x. And then we know that it has been given by the, who is this person, is D'Alembert. Ronald D'Alembert has given the, initially he said that it can be a superposition of this wave solution, can also be a solution to this equation, where you have a pi of x plus t, pi of x minus t, plus this integral over x minus t to x plus t. There's some printing mistake here. That doesn't matter. So depending on these conditions, you can apply. Either you can have this or you can have this, depending on this. Then corresponding solutions can be obtained. For example, in this case, the second term, this is 0. First term is existing. And with the superposition, you can get this u of xt. This is cos of x plus t plus cos of x minus t. If I simplify, it is a cos x into cos t, not the minus. This is a mistake, printing mistake here. Another possibility is cos x will be there, you integrate over it. Okay, so that's what the second part, which is with respect to the time derivative, is the condition. Integrate it, you'll get this result. Both are one and the same. Okay, cos x into, only the phase is differed by 90 degrees, that's all. The features are same. This is what your first part of it. Simplify, this is what you'll get it. If you make a plot and as a function of time, you see how nicely the wave function is, wave equation is evolving. This is what your oscillations of the phase, which is when you go for oscillators, we can describe this all allowed mode, not allowed mode, all these things that are possible. Okay, as a function of t, this is what is going to happen for this wave. When I add this, I get this. That's what being plotted. And of course, we have a velocity term. If you want, you can retain it. Otherwise, just for a demonstration purpose, you can make it as 1 unit of that. So this is what really the wave equation, and its motion is like this. Okay. And you can verify, of course, by substituting them. You can integrate and check it also. And integrate the solution also will satisfy. Then again, you can check with the other solution also, and then make sure that, you know what happened. I'm just replacing this solution initial condition with the sign h of t also, that also being satisfied. Okay, and you can substitute and confirm it. That's also will satisfy. This is what the sin h nt into sin nx. So the given n equal to 1. You have n different values also. It will only increase your number of modes that you have here. Okay. And this is what your sin nh of t. This initially will be like this and goes on, plays out, then goes on. That's what actually means here. It is what they see. Playing out, then picking out again back. Okay, the whole thing goes up and down, vibrates, vibration period. Similarly, heat equation here, you can see this is the so-called the Fourier series with this time-dependent component. And that is the one which play a role here, and that's what is responsible for this. Heat will be dissipated for a given geometry of this plane. Initially, this is distributed like this, and as time goes on, this is what really happens with respect to this solution, what you have here in terms of the Fourier series with this term. Okay, and of course, as I said, if you increase the number of terms, then it would be nice to see that there is going to be a sharpening of this tips. That's going to happen. Okay, so now here is the heat equation in another form with e power minus x squared again. As I said, this is the starting exponential square of that with respect to this 1 plus of t square root of that. That is getting decayed. You can see here, probably you can start it and check. Sorry. What happened to this? This is what my initial condition here. Instead of sine, I'm having exponential. And the solution is of this type, and the solution is decay. This is also fine. Okay. Also heat equation or diffusion equation. That this can be shown in a two-dimensional plot. The width is getting increased with respect to the time goes. Okay. And then triangular structures, that's also possible to analyze them with the, instead of a specific function, you can have a triangular wave and then make a plot against the thing that's going to happen. Again, this is the, so this is PD multiple solutions which are already indicated. Okay, this is satisfied. Linear sum is also a solution to this. That also has been explained. Transport equation already I have explained there. QH is also has been explained, and this is the eigen system. And I wanted to introduce to you one more, which will be of useful when you have a partial differential equation. And I see that. Okay, I'll just find out how. Yes, you can go directly instead of searching for it. Put the question mark now. D solve value. This is another interesting thing when you have a PDE. D solve one, and you can use eigenvalue, D eigen systems, D solve value, which is meant for the solving the partial differential equations, that also important for you to check and use them. You can solve the ODE also and PDE also. See here, y double prime here, please solve the single variable. And you can go to Mendel generalization extension, linear differential equation, non-linear differential equation, system of linear equation, differential algebra, delay differential equation, piecewise differential equation, hybrid differential equation, Sturm-Liouville problems, integral equation, first order partial differential equation, hyperbolic, partial differential equation, parabolic. See, everything, most of the things which is available, standard stuffs are available for you. Now, if you wanted to analyze anything new, just look at the physical problem. If you need any additional term with that, how do you do? It all depends on the nature of the problem that you have to see. Now, it almost covers all this PDE requirement. Okay, select this hyperbolic, then look at how many systems that have been given. Okay,
All are already inbuilt in Mathematica.
already built in. So much has been done. That's what I said. It's a big area on its own. Most of the things that are available. Only thing we should understand and grab it and use it for our computation purpose. That's all. General partial differential equation, partial differential equation over regions. There are other options and some applications, some 30 applications is mentioned here. Ordinary differential equation, hybrid, delayed differential equation, integration. There are some people that are talking great about it, but he has done a lot on this already. Delayed differential equation, classical partial differential equation, general partial differential. See, you just name anything that's almost available for you. And you have to take it to the next level. Only thing, you have to have a physical situation. There is a demand for you to understand additional terms and how that additional terms that's going to influence, and is there any extra physics or physical information that's available. That is available, then it's going to be a great contribution in understanding the physical problems. So it's fine now. I think we can have some questions. I hope that you might have enjoyed the course. I hope.
Yeah, really, sir. Though
Yeah.
the COVID situation make us
Yeah.
away, but we could join together and we could learn a lot of things
Yeah.
through
It's a lot
online
fun.
class.
Yes.
Otherwise, we will miss all these classes from you.
Yeah. That's true. And I also get a satisfaction. Yes, something has been done to the students where they are having an they see, though there is a limitation, but still there is an exposure. No,
Yeah,
this
really, sir.
this
Really.
matters a lot for them also. Because they
Yeah.
know that such things are available. When there is an opportunity, definitely they will explore them.
Yes, sir. Yes, sir.
Yeah, so that's what really matters ultimately. See, I have seen there are dissertations. Okay, MSc, one PD alone, one MSc project,
Okay.
just one PD. For example, transport equation. Now
Yes, sir.
that's an MSc project worth of about 45 pages. Lot has been done, and similar things can be done which are closely connected to the physics problem. Select them physics problem, then give
Yeah.
it to them, and then ask them to work only on that. By the process, now what happened? He has to learn so many things. He should have some sort of an understanding about ODE, and then come to the PDE, then physical situation, initial condition, boundary condition, and how these boundary conditions are influencing the initial condition influences. Okay, so everything will definitely give a deeper and deeper understanding, and he will force to learn not only his problem, there are other related problems because he has to have some understanding. Then only it's possible to come out with some interpretation for this mathematics he's trying to do through this PDE. So PDE is a very big area, really. Okay, and
Yes.
it brings out so many things. In fact, Dirac equation, no?
Yeah.
Dirac is very strong in PDE. That's why he would able to solve this spin problem, no? Through this so-called Schrodinger equation, no? Which is long pending for people, no? Spin,
Yes,
no?
sir.
Interpretation for the spin is a very great puzzle through the equation. But he is so strong in his PDE, no? And he made a modification, bringing a complex into the system. Okay. Then then he looked at and finally found that something great happening. That's how things, when it go deeper and deeper over that on particular issues, we will daily make some sort of a breakthrough in understanding things. It can happen. I'm sure these equations contains so much of problems yet to solve. Okay.
Yeah, right now I am realizing that because of your strong mathematical background, you could contribute in dielectric spectroscopy by
Yes.
giving
Yes.
your
That's
model.
that's how it goes on. Because you need to have somewhere some strong points, no, for us to say. That will be possible by spending. The issue is only one: understanding the exponents in physics, dielectric physics. That's all. Very, very simple. Only one sentence. We wanted to understand what is that exponent means. Okay. Now, no, I really feel that we have to really look for the fractional derivatives, fractional calculus.
Yeah.
And I have started collecting books. I find there are 10 to 12 books available already. Fractional derivatives. People are struggling to understand what is that really happening. Because we have been talking about d square y by dx, dy by dx. Okay. Now, suppose
3 by d square is 3 by 2.
not only that, d of 0.1 u divided by dx of 0.1. What does it mean?
Yes, sir.
And if I take it to the incremental level and then take it to the 1. So whatever the results which is available for 1, you should be able to get it with the method what you are going to develop now.
Yeah. That must be converged to
the results what is available. So then that's going to be very challenging results now. And mathematics also challenging. And also your geometry, what we are talking in the linear vector space, no? Okay?
Yeah.
That should be changed. That is where your definition will be getting modified. You have to really look for what could be the alternate way of looking at the linear algebra when they are not parallel and perpendicular and evenly spaced. If it is, if you get the point, if it is a wiggling, x and y,
Just
what
like
will happen? What would happen now? And how do you define your basis vectors? 0, 1, 1, 0, 0, 1 is a base vector. What happened to the base vectors now? So those things all, there must be a way of looking at things now. Because reality is, it's not like what we are trying to understand now. In a real situation, you can have a unevenly spaced parallel lines will be there, and it need not be a line; it can be a curve of any type. So those things are still a puzzle. Because in real situation, for example, dynamics, what we are looking at in fluid dynamics, it is not like what we have thinking now. It's exactly like parallels. That is a limited scope for it, because it's not really show. So therefore, there are opportunities for us to think and then try to bring out something very challenging results, which will be extremely useful for the later stage. One breakthrough is enough. Like Newton has given limits. Newton's law is not important. Okay, his mathematics that led to this conclusions. The law has been arrived after getting the strong mathematical background of these limits, derivative and integrations.
Yes, sir.
That is what led to him to formulate this laws. So that is more successful than this laws what he has identified. So you can really
Yes,
feel
sir.
that there's something great has happened. Okay, so students, they are enjoying now. How many are there
Yeah.
now?
Right now,
11.
11.
Yeah, all are busy with their own schedules.
Sir, may I ask
Yeah.
you a question?
Please.
Yeah, about the plot that you shown before.
Okay.
Why you use animate instead of any kind of manipulate or graphics?
Animate. Okay, that's.
Is there any
Yeah.
criteria like you can only use?
No. It's not like that. You can write same thing can be done as a manipulate also, because manipulation also can be done with 0 to 5.7. They are one and the same. But this is if I have animate false. If I give animation is already ready with it already. Okay.
Okay.
See, for example, look at this. I have not executed, but it is going to work now. Did I repeat it now?
Okay.
It is no input given, but still it's working. Animate takes care of that. If I use the manipulate, that's not possible.
Okay.
Okay, manipulate means you have to have all the inputs requirements should be there, satisfied, and it should be available for you to animate it. Now this is not necessary because animate is already stored in the animation form. It is available for you to use even without executing. Once you execute, it will be available for you to use. Animate, which is available as long as you are here. Okay, after execution, if you go out and come back, again that's not available. Whereas this will be available for you. Animate dynamics requirement. If you put test, then it will automatically animate. And here I have given animation running false. If it is, if this is not given, it will be running all the time. Once you open the file, it will be start running. Till you close the file, it will run. But if I use animation running false, it is under my control now. Whenever I need, if I can click it, it will be animated. So that's why you have animation running false. Once you click it only, it will work. If I don't have this, once the file is opened, it start animating it. Until I close, it will be animating. So that's also not necessary.
So that's the difference?
That's the difference, yes.
Okay.
And this animation rate also, you can have a control. What is the rate with which you wanted to see? I made it as 1. You can have a 0.5 or 1, 2, 3, 10. If I make it 10 also, you can see there's going to be a change. Okay. So that's also can be controlled. So it's possible to do with the control over all these parameters what you have. Yes. Any other questions? Okay. Will we close down?
Okay, sir.
I
Thank
enjoyed
you
the
very
course.
much once again.
I enjoyed the course, man.
Yeah, really, I got a lot of yeah.
Yeah, maybe I'll send these things. Maybe this compilation will be definitely useful.
Yeah,
And
really, sir.
I think proper compilation will be of much useful for so-called document, nice document.
Yes, sir. And
Okay.
you can suggest some reference,
Yeah,
name
I'll
of
suggest.
some reference books.
Yes. I'll suggest some of the books.
Okay, sir.
Okay.
Okay, sir.
Right.
Good night.
Thank you. I'll close the session now.
Okay, thank you, sir. Good night.